We will now do two example problems for Chapter 30. One be a collapsing magnetic field in a coil, and the other is a force on a bar moving in a magnetic field. So for the first one, imagine that we've got just a coil or a loop of wires, just a whole bunch of wires here. So we can say that this is 25 turns. Okay, and to make the math easy, it's in a circle. And so the radius of the coil is going to be 12.7 centimeters. And let's say there's a magnetic field that is into the page throughout here. And the magnetic field goes perpendicular to the coil. And the magnetic field is 0.316 Tesla. Okay, and now the magnetic field is allowed to collapse. So whatever's making the magnetic field is turned off, and so the magnetic field goes from 0.316 Tesla to 0, and it does that in 0.145 seconds. And so the question is, if this coil wire has a resistance of 2.25 ohms, how much current flows in the coil as the magnetic field collapses? So what's happening here is that you've got the magnetic field going through this coil, and you've got a flux. And now the flux drops from whatever it was to 0 in 0.145 seconds. And so by Faraday's law, that's going to induce an EMF in the coil. Since the coil has resistance and it's a closed loop, that means that there's going to be current. Okay, so Faraday's law tells us that the EMF is minus N rate of change of the magnetic flux. And so, so what we've got here is the magnetic flux is going to be equal to, magnetic flux is equal to magnetic field times the area. So in this case, that's going to be B times pi r squared. Okay, and so the EMF is going to be minus N dB dt pi r squared. Now, if the magnetic field collapses uniformly, then that's going to be the same as delta B over delta T. So in other words, if it all drops at the same rate, then the derivatives are going to be the average of the change over the change of time. So the EMF is going to be minus 25 times the change in magnetic field, 0.316 Tesla, divided by 0.145 seconds. Okay, times pi times 0.127 meters squared. And that comes out to be 2.76 volts. Well, the current is going to be the EMF over the resistance. So the current in that coil would be 2.76 volts divided by 2.25 ohms. So the current is going to be 1.23 amps. So that is the current in that coil as the magnetic field collapses. So the next question would be, if I were to have like side view of the coil, so there's the side view, if instead of the magnetic field being directly into it like a head, what if, there's your coil side view, what if the magnetic field were into the coil like that, and so the magnetic field were into the coil at an angle, and the angle was, let's say that the angle was some theta relative to perpendicular? Well, all that matters is the magnetic field, the perpendicular component of the magnetic field. So in that case, instead of the B, it would have been B cosine of the angle. So if the magnetic field had been at some angle instead of directly in, instead of using B, then the flux would have been, instead of B times A, it would have been B times A times cosine of the angle. In this case, that angle was 0. It was directed perpendicular, so the angle relative to the normal was 0. So we just used B times A. Okay, the other example that I wanted to talk about, and that was, suppose that we have a rail, resistor, we have a rail, we have magnetic field directed, in this case, out of the screen here. So the magnetic field is directed out of the screen, and I have a bar that I'm pulling that way with some velocity. So let's say the velocity is going to be 3.26 meters per second. Let's say that these two rails are 0.75 meters apart. Let's say that the resistance over here is 1.25 ohms. And so I want to know, what is the force on that bar as I'm pulling it? We say, why is there a force on it? Well, as I'm pulling it, then what happens is, by the right-hand rule, we have an EMF this way. So that means the current is going to flow in that direction. And so that means there's current flowing in there. We know there's a force on current. The force equals ILB. And so there's going to be a force on that bar due to the current flowing. So then we say, well, how much current flows? Well, we know the current is going to be the EMF divided by the resistance. So how do we find the EMF? Well, this is motional EMF. So the motional EMF is going to be the velocity times the length of the thing times the magnetic field. Okay, so that means the current is going to be equal to the velocity times the length times the magnetic field divided by R. Okay, so that gives me the current, and then the force, which is ILB, is going to therefore be V L squared B squared over R. So the force is going to be equal to 3.26 meters per second times L, 0.75 meters squared, times magnetic field, 1.15 Tesla squared. I think I forgot to tell you the magnetic field, but we're assuming the magnetic field is 1.15 Tesla. And then all that divided by the resistance, 1.25 ohms. And so the force is going to be 1.94 newtons. So that's the force it would take to keep that bar moving. If you're not applying that force, then it would gradually slow down. And this is related to the example that we did in lab, in which I had the hollow aluminum tube, and I had a magnet that slid down it. It induced electric currents that then had a magnetic field that resisted the change the change in the flux, and so those are eddy currents. And so this concept here is related to how magnetic braking works. And it was another application of Chapter 30 concepts.